The free energy change of a reaction can be found by summing the free energy changes of formation of the products and then subtracting the sum of the free energy change of formation of the reactants. This reaction looks very familiar to you, this equation, perhaps because you've seen the heat of a reaction is equal to the summation of the heat of formation of the products minus the heat of formation of the reactants. So recall that heat of formation is the heat to form 1 mole of a substance from its elements in their standard stable form. So, for example, the heat to form a mole of carbon dioxide, so the heat of formation of carbon dioxide, is the heat of the reaction in which you take a mole of carbon in its solid graphite form, the typical standard form of carbon on Earth, and take another mole of oxygen gas and react them together. That heat of that reaction is the heat of formation of CO2. Now, what about the heat of formation of O2 gas? Well, in order to form O2 gas, you have to form it from its element O2 gas. And in fact, there is no change in that reaction, so the heat of that reaction is equal to 0, and hence the heat of formation of oxygen gas is 0 kilojoules per mole as well. The heat of formation is 0 for elements in their standard stable form. So on tests, you might be given the heat of formation of compounds like carbon dioxide, but you won't be given heat of formation of compounds like, or elements like oxygen gas. But the rules for heat of formation are similar for the free energies of formation. For example, the free energy of formation of oxygen gas is 0.0 kilojoules per mole, just like the heat of formation of oxygen gas is 0.0 kilojoules per mole. So we can plug in the heats of formation, actually the free energies of formation of things. For example, we already saw in a problem earlier, for the reaction of the decomposition of calcium carbonate to give calcium oxide and carbon dioxide, is that reaction going to be spontaneous at 25 degrees Celsius? One way that we could solve that problem, as we did previously, was solve for delta H and delta S. But in this case, we could also use the free energies of formation of the products and reactants. They're provided to you here, which can be found in the appendix of your textbook. So plug in for the free energies of formation of all these compounds, being sure to account for the coefficients in the balanced chemical equation. You get the free energy of formation, actually free energy of the reaction change is 130.2 kilojoules per mole, extremely similar to the value that we saw previously in that last video. So is the reaction spontaneous at 25 degrees Celsius? No, we have a positive delta G of reaction, so it's non-spontaneous. Consider just kind of another topic. Let's say that you were to release some natural gas into a room. So a pipe is broken in your apartment. Now, it's in the presence of oxygen, and it can react spontaneously with that oxygen to provide carbon dioxide and water. Now, is this reaction actually going to occur? We know that it's spontaneous at room temperature, but will that reaction occur if you just release it into the room? Well, the answer is no, not without a spark. You see, even though this reaction is spontaneous, because for a large part it releases heat, it has a negative heat. This reaction, in order for it to begin, it needs to have a significant enough kinetic energy of the particles so that they can overcome the activation energy barrier. Now, at room temperature, none of your particles, or very few, will be able to roll over this hill. So none of them will be able to react and release this energy. But if you provide a spark, then some particles near to that spark will have a high enough temperature so that their kinetic energy is high enough so that they can roll over the hill. They can overcome that activation energy barrier, and so doing, they can release heat. And when they release heat, they increase the temperature of everything else nearby, which allows everything else nearby to react as well. So, provide a spark. Near to that spark, you'll get some reaction, which will release some heat, which will heat up everything else so that everything else can react, which will heat up everything else so that everything else nearby can react. And so your explosion starts at one point, but it spreads quickly until you've consumed much of your reactant. So even though a reaction is spontaneous, that doesn't mean it's going to occur necessarily. It needs to overcome the activation energy barrier. On another topic, this weight, can it rise spontaneously? No. Things are naturally drawn by gravity towards the Earth. Yet, you can make this weight rise. You can make this non-spontaneous process occur by coupling it with a spontaneous process. A larger weight, which is attracted to the Earth, will go down, and so doing, and being attached to the other weight through a pulley system, it can draw that weight up. We see that we can drive this non-spontaneous process by coupling it to a spontaneous process. That spontaneous process did work, which caused the non-spontaneous process to occur. In more chemical examples, we can see that in the body, glucose can be metabolized, and that will produce carbon dioxide and water. Now, this reaction, it has a negative delta G, so this is exergonic. This is exergonic. It is spontaneous. It can drive endergonic processes in which you have a positive delta G, in which the free energy increases, and that can only be done by work. So when you metabolize glucose, this can allow for ADP to have phosphate attached to it to form ATP, and this ATP can later be used to turn back into ADP to lose free energy, and coupling that with amino acids, those amino acids, they can turn into proteins by this release of free energy. You can drive this non-spontaneous process by coupling it with a spontaneous process. Similarly, again, we have here, you can burn methane, which produces carbon dioxide and water, and this releases free energy. And that free energy can be used for the decomposition of aluminum oxide, bauxite. You can break aluminum oxide through electrolysis into pure aluminum and release oxygen gas. Electrolysis. All right. Thanks for watching, guys.